guys, today we're going to do a little bit of a review about complex numbers. So we've talked about how I would find all the real zeros of a function. Knowing about how complex numbers work are going to help us figure out how to find all of the solutions, including imaginary solutions to some of our polynomials. So your central question today, Bill, is how do I simplify expressions with complex numbers? So we're going to start by talking about what is a complex number. Your complex numbers are going to be in the form a plus bi. So this is the general form of a complex number, a plus bi. And that I actually has a definition, and the reason we defined it is so we actually could say something about the square root of a negative number. Before, that didn't exist. So I is just a definition that is equal to the square root of -1. And so, for instance, we could take the square root of -9 now, and originally the square root of 9 is just 3. Well, now I can take that, and I know that I can actually not get an error out of my calculator if I have that guy. So we just have 3i. Now if I took -1 and I squared it, I squared, that's going to be -1. If you square a square root, your square root goes away. Then we have I cubed, which I could rewrite as I squared times I, right? I to the first, so we'd have 3 different i's in there. Well, I just defined I squared as -1, and I, we know, is just I, so I cubed is the same thing as -I. Okay, and then finally I to the fourth, we could rewrite as I squared times I squared, which would be -1 times -1, or just +1. Now, if you kept this pattern going and you did 5i, I to the fifth and I to the sixth, this pattern is going to repeat after this point, and it's just going to keep going. So I to the fifth would be equivalent to I to the sixth would be equivalent to I squared, and it just continues on. So the really nice thing about this is that as long as I can find my multiple of 4 and think about what the remainder is for that number, I can automatically simplify down. So if I look at this example, simplify I to the 23rd, well, I know that this would be equivalent to I to the 20th times I to the 3rd, because 20 plus 3 is going to give you 23. Well, I know that this is a multiple of 4, which is just 1. Okay, so this is I to the 4th 5 times, which is just 1 times 1 times 1. So that's just going to give me 1. This term is 1. And I just defined I cubed as -I. And so I have 1 times -I. So this simplifies down to just be -I. So again, think about numbers that are multiples of 4. 20 is a multiple of 4. And then we go ahead and we write pretty much what our remainder is, and that would be my answer. So let's talk a little bit about some of those operations with those complex numbers. First one is those addition, subtraction. And honestly, this works almost exactly like how your polynomials, when we were simplifying those things. You're going to find your like terms and combine them. Hardest part here is when you have to use this distribute of the negative. Again, I like to just take this minus and plus, just change all the signs in the second set. And now all you have to do is combine the real part of your term, so 6 and -2 is 4, and then you combine the imaginary part, or the i's together, so 3i plus 2i is 5i, and I'm done. Okay, that's in the form a plus bi, we're happy. So it gets a little bit trickier when you have to multiply, but again, this is just FOIL, this is just that double distribution, where you take everything in the first term, and you're going to have 6 times 2 is 12. 6 times -2i would be -12i. And then down here we'd have positive 6i, and then -6i squared. And now I have to go in and combine like terms. Now the one thing I know from that chart with all the i's on it is that I squared is just equivalent to -1. And so really here I have 6 times -1, or just positive 6, which is really, really nice, because then I don't have to worry about figuring out what to do with that I squared. So really what I have here is I have 12 plus 6, right, because that sign would change, minus 12i plus 6i. Combine my real parts together, so I'd have 18. Combine my imaginary parts together, minus 6i, and that's my answer. remember, I squared equals to negative 1. This one right here, when we do division, so we have 3 plus 2i divided by 6 minus 4i. It's kind of like with the radicals. You're not allowed to keep a square root down in the bottom or cube root or whatever. We're not allowed to keep i's down at the bottom either. And this is going to be exactly like when we multiplied by that conjugate, but we have what's called the complex conjugate now. Basically, it's going to be the same thing as the bottom, so it's going to be whatever. We'll have 6 and 4i, but you just change the sign on I. Okay, gave myself a little bit more space here. So if I'm going to take this expression, and this is the one that they gave me, struggling with space today, and I'm just going to multiply by a tricky form of 1, where I'm going to take the 6, and then I'm going to change the sign on the I. So it's going to be the same exact expression, you just flip-flop the signs. And we did this when we were doing the trig stuff too. And then it's just some more FOIL. Okay, and so if I FOIL this out, I'm going to get 18 on the top plus 12i plus 12i plus 8i squared. And if I FOIL on the bottom, I'm going to get 36 plus 24i minus 24i and then minus 16i squared. And so the cool thing about the conjugate, and we saw this when we were doing our proofs, is that this is going to make those guys cancel. And so then I no longer have any i's in the bottom because I know that I squared is actually negative 1. So at the bottom I really just have 36 plus 16, which is going to get me 52. And then and the top part, again, I squared is just negative 1. So I'd have 18 minus 8, or 10, and then 24i. Okay, this is a great answer. You could simplify this down a little bit, and what I like to do, since I'm looking for something that's in the form of a plus bi, that looks like a t. I'm going to go ahead and I'm going to split this fraction up, and I'm going to have 10 over 52 plus 24 over 52i. And we're allowed to do that, rules of fractions and everything. And then I can simplify my fraction down a little bit, and I would have that this guy would divide by 2, so 5 over 26. And then this one would divide by 4, so 6 over 13i, and then that's in that form that they always ask me to simplify to, number plus something times I. Okay? One thing I did want to clear up, a misconception that sometimes we have about using I in a multiplication problem, is when I normally have square roots. We remember back when we had to simplify this down, like root 2 times root 3 would be root 6. Okay, that's nice. And so if I look right here, I would have this guy is root negative 2 times negative 5 is positive 10. But that's not true. Okay, that's lost a part of your answer. If you think about this, if I simplified negative root 2, that's actually I times the square root of 2, because this would be negative 1 times 2, so you can take the square root out there. Okay, times, we would have that same thing, we'd have I, but now square root of 5. If I multiply this together, I have I times I, or I squared, times now 2 times 5 is 10, which actually gets me negative square root of 10, because I squared is equal to negative 1. So before you start doing any operations using the square root of a negative number, change your stuff to i's. Okay? So before you start doing any sort of operations, multiplication, whatever, addition, subtraction, change these things into i's, so that way you won't lose your answer or get the incorrect answer. Okay? And here's the whole reason we're doing this. If we want to find the solutions of the equation, originally I might try to factor this equation out, and I know there isn't anything for sum of squares. This looks like something cool, but sum of squares doesn't work. We need a difference of squares, and then I can do stuff. So then maybe I want to think about subtracting 36 from both sides and doing x squared equals negative 36, and then take the square root. And originally that wasn't going to work. And if you looked at this calculator, you'd see that this was that function that was like hanging out up here. It didn't have any roots. but it does have some imaginary roots. So remember, now I would have that this would be 6 and then I, and the only thing we have to be careful of is when I take that square root, I'm going to have a plus or minus in there. And so those would be the solutions to this. Okay, and that works in the quadratic formula. If you had something left of a negative underneath the square root, then you could just use your i's in there. Okay, and so tomorrow we're going to practice our complex numbers a little bit more, and I will see you then.